So, in this part I will talk a bit about high-performance computing, and you will also see how you can use your own applications, if they're written in Python, to run on large systems. So in this case I will be talking as the director of LUNARC, which is the High-Performance Computing Center at Lund University. And I will give an introduction what high-performance computing is and why you should use it and when. So the talk will be divided into several parts here. So I have an introduction, some history, architectures, Linux and HPC, statistics, kind of notion how the HPC has changed over the years, how you use clusters, some history of LUNARC, and some conclusions. So what is high-performance computing? So this is the kind of definition here, and this is the fastest computer currently available, used for number crunching, scientific computations, animated graphics, and so on. My definition is more simple. So it's because supercomputing is time dependent. A couple of years ago, a laptop would consider supercomputing. So I usually name it a computer that offers greater capacity than a desktop computer offers at present, or has more properties that a normal computer architecture can't offer. So for example, if you have a laptop and you have a data set that is larger than your memory in your laptop, then you perhaps need to consider, where can I find a computer system that can handle my data? So then you perhaps need to go to supercomputing to look at that, because most of the computers we have, for example, at LUNARC, have at least 256 gigabytes of memory per server. We also have some servers that have 1 terabyte of memory, not disk, but memory. So, and also if you want to do a parameter study, like we are doing in this course, say you have 1,000 parameters you want to study in different combinations, that can take a long time to compute. If you have a supercomputer, you can actually do many of these parameter studies at the same time, because you have multiple computers that you can run in parallel. So that is a very simple term of parallel computing, is that you can run many things at the same time, and you can produce results faster. Yeah, so why do we need supercomputers? So, as I said before, there are many problems that require large resources today. We can't wait for the computers to get bigger. You need to kind of solve the problems right now. You can also, faster computing can also provide the ability to make more simulations faster. And for example, one thing is you simulate cars, the crashing of cars in the computer instead of real life simulations or real live experiments. You can also provide ability to make simulations faster. For example, you need to be able to make a prognosis for the weather in time. You can't wait for 2 weeks to get the prognosis of 1 week. You need to make it now, and then you need to have the compute power that can do that fast enough that you can get results when they are relevant. So I touched upon where we have used of supercomputers, for example, in meteorology. There is a large computer in Linköping that is funded by SMHI that makes a lot of the weather simulations that produce the weather forecast we have today. And there's actually connected in parallel with a Norwegian computer as well. So they actually share resources. So the Norwegian simulates the weather in their region, and then they connect with boundary conditions to the Swedish forecast. So we can make better predictions in the entire Scandinavia. And these computers are really big, like 400 or 500 servers that are connected together to make these computations possible. Another area that requires large computation is crash simulations in car design. To make this realistic, you need to have a large number of elements, and these equation systems are really, really large and can only be solved with large computers. So with this, you can actually replace a lot of the experimentation the large-scale experiments crash test with simulations. You can't entirely replace the real experiments. You need to calibrate the simulations. An excellent example of that going wrong is the Mercedes A-Class. That was the first car that actually was completely simulated in computer, but they didn't make enough real experiments, so the computer, the car was unstable. So you need to kind of calibrate the simulations as well. You also have a large area that actually one of the biggest users of HPC in Sweden today is fluid simulations. So that can be a combustion simulation on the left side. It could be wind tunnel simulations on the right side here to see the turbulence behind an edge of a vehicle or something. It also requires a large number of computers to do this, because if you want to have high resolutions, you need to have much more elements to resolve this. So, and more elements, larger computers. Medicine is also fairly well used today. So I think 70% of our computers at Lunark is mostly, it's chemistry. So this is medicine, but we have 20% of our usage is actually from medicine. And that is DNA analysis using different tools, statistical analysis and stuff like that. Mechanics is also something like 10% of our usage of the Lunark resources. And here is a simulation of pulp forming. So when you make paper, you need to crush the wood, and that is very energy costly operation. So using mechanics, you can simulate this process. Buckling simulations. And as I said before, chemistry is really large. It's about 70% of the complete usage, and that is molecular simulations. Those are more molecules, longer time scales, larger computations. So a little bit about HPC history. So we are going all back to 1964 until now and see how things have evolved. So in 1964, one of the first supercomputers was built, the CDC 600. The performance was 9 megaflops. And what does megaflops mean? So megaflop is million floating point operations per second. And if you compare today, I think this is already too old. We are in 100 gigaflops per on a PC today. So we are much higher than this. And you can see this is the size of the computer room. So there's a lot of cabinets. There is a lot of storage devices here. Actually, a form of actually quite modern input terminal with CRT tubes, TV screens, printers. Usually they had a kind of teletype terminal where you entered with a printer that you enter commands to. But so this was quite advanced here. 69, we had CDC 7600, we had 40 megaflops. Still a lot of computers. We're not even close to a PC today. 1976, we had a Cray 1, 160 megaflops. And we actually had one of these in Sweden, in Linköping. And it was used to design the JAS Gripen aircraft. So it was one of the first in Sweden. It was, at the time, very controversial thing because US didn't like Sweden at the time. So they had it has to be locked in a certain room and with a lot of protection because they didn't trust us. So, but we managed to get it anyway. Then 1980, yeah.
Do you know how much it costed back then for Sweden to buy?
Today, I think it's, if you compare it today, it's something like, I'm not sure about this because I think it was used at the time already. So it was a used Cray that we got.
Yeah.
But the largest computer in Sweden today is like 150 million Swedish crowns. And the new one that is being built in Linköping is going to be, I think, 1 billion Swedish crowns. I think it was in the same ballpark at the time, if you change the values here. So we got a 1982, we have a Cray XMP, 235 megaflops. So they were designed really strangely because they were liquid cooled. So the motherboards was actually floating in fluoride, something, to make it cold, because they were so hot, so that they needed to be cooled. So they were kind of in the round ring here to have tight communication between the different electronics. 1986, IBM produced something called IBM 3090, and that was actually one of the first supercomputers at Lund University. And the VPF stands for Vector Processing Facility. So it's actually one CPU, but it can process vectors in parallel. So it had a array, and it can do computation on a single arrays with all the numbers at the same time. So it was a parallel vector machine. So 110 megaflops. 99. Now we are getting into PC territory. So in 1989 we got the Cray YMP. It was 2,144 megaflops or 2.1 gigaflops. 1993 Cray T3D, 13.7 gigaflops. So up until now, most of these machines were specially built to be really fast, or also called mainframe. So they were very expensive machine, very special, their own processor architecture and everything. So, and that is about to change. So in 1997, the US had a project called ASCII Red, and here they try to build supercomputers with normal computing parts like rack-mounted servers, with normal interconnects like network connections. So not purpose specifically designed to be a supercomputer, but using normal hardware. So now we're at 2.38 teraflops. In 2002, the biggest computer was built in Japan, and it was the Earth simulator. So Japan has a lot of problems with their weather, so they put a lot of money into a big computer for simulating weather. Now you can see these are racks that are like 2 meters high, and it's almost like a football field filled with computers. Then in 2004 we got Red Storm, which was let's see here, 41.47. I don't know why it goes away here. Teraflops, and just like many US projects, there is a military connection. So the red and black things here are partitions that could be physically separated to do military computations and civilian computations. And they could actually be disconnected by special mechanical disconnects, so they were physically separated. 2005, IBM came back in the market here, and with a special processor architecture that you can also see in the PlayStation console. So a lot of smaller processors that connected together to create a machine with between 135 and 600 teraflops. This is actually one of our computers here, called Alaric. Let's see. Well, I'm not sure why this does that. 2012. It's an AMD machine with something like 40 teraflops, built with AMD processors. Each processor had, let's see here, each server has 16 cores. This is the Jaguar Cray again, 1.64 petaflops. And now you can see the huge scale of these things. And the left side here, this is cooling. And that is something that to do these computations, you really need to be close to a power plant. So we are talking about gigawatts here in power. So Lunark, we are not that close to. We are around 220 kilowatts in power on our machines. We have like 250 servers. So supercomputing takes a lot of power. We would really like to have reduced this power footprint because it's expensive. The Roadrunner was a power PC. Let's see here. 1.7 petaflops, built upon a power processor, which is not an Intel-based processor, but an IBM-specific one. In 2016, we built Aurora. I'm not sure why this does this. 240 teraflops. And at the time, we actually built in LED lighting as well to make it cooler. So that was built on 20 core Intel CPUs per server. Roadrunner, Stampede, 19 petaflops, Texas Advanced Computing Center. And in 2023, we released Cosmos, and we actually achieved 1 petaflop in Lund. And now in Sweden, we are aiming for, I think the new machine will be something like 100 petaflop or something. It's a lot of floating point operations per second. So, a little bit short about architectures. So, there is a lot of different architectures in supercomputing. So, if we start here on the top here, you have something called single instruction, single data. That is a normal computer. It takes an instruction, works on data, and continues doing that. You also have an architecture called single instruction, multiple data. That is when you have one single processor, each instruction can work on arrays or vectors simultaneously. Then there is nothing called multiple instructions, single data. But then you have multiple instructions, multiple data. That is more common today. We have multiprocessors, which is the technology we have today. We have multiple servers. They share memory in different ways. So this is multiprocessor. Usually, what you have in your laptop, you have, for example, 4 cores. That's a multiprocessor, and it shares the memory in the laptop, so you can have 4 simultaneous programs running on your laptop at the same time. You can have more programs running, but they share the same processor, but you can have 4 simultaneous threads running. Then you can have multi-computers. That is what we have in our cluster. The Cosmos cluster is many multi-processor computers connected together in a network. And then you send messages between these computers to share memory between or data between the process when you're running. So these are the 2 ones you have. This is what you have inside your computer. You have processors here. They share memory here. So each of these are a CPU. So if you have a laptop, these are your cores that you can see, and they all share memory. And then you can connect them together in a network. So you have a processor here or a computer with memory, and then you have a networking here, and you scale then you send messages here. If I want to access memory on this machine, this computer can request that memory, and you send messages between these to communicate. And that is what we have in Cosmos. We have a lot of servers that have processor and memory, and they communicate over a network. You can connect the networks in different ways, depending on how well you want to communicate. You want to have the shortest path between the servers at the same, so that you don't have to jump between a lot of computers to get to a machine. So you can see here, you can have cube-like structures here. You can have hypercube-like structures here to create short paths to the different machines in your cluster. And also, the idea about having a lot of servers at the same time in your computing is that when you increase the number of processors that you have, you can scale up the performance. So ideally you want to have, if you add CPUs, you want the speed up to be linear, and that is the best case you can have. But usually with different programs here, it's not all programs scale as well. So you can see here that in the n-body problem, like molecular simulations, you can scale almost linearly, but it drops off the more processors you had, and that has to do with the communication between the processors, that the network becomes saturated and in a bottleneck. And then some applications here doesn't scale at all. So it scales up to 10 and then it kind of drops up the scaling in. And at that point, it's not useful to add more processors because you won't get any more speed up. So in that case, if you know that you have a problem like that, you should stop in time because it's really just waste of resources to add more processors. Then also there is networking, and here for supercomputing, this term here called latency. That is the time it takes to initiate a message, because sometimes you need to send a lot of messages between computations, and if it takes too long to communicate, the computation has to wait on the network, and that is really detrimental. So the speed in memory is really, really much, a magnitude higher than communicating over the network. So you need to really ensure that you communicate efficiently and fast over the network as well. There are some network types here. We can have gigabit Ethernet, 1, 10, 40, and 100 gigabits per second Ethernet connections. And on Lunark, we have had all networks. So a long time ago, we had 100 megabits, we had 1 gigabit, and we currently have actually 100 gigabits, something called InfiniBand. That is the next cluster is the Cosmos cluster, and we have 100 gigabit between the servers. So you can move data between the servers quickly. Skip that one. So this guy is actually the father of supercomputing with Linux. So he realized that at some point it was really expensive to buy supercomputers. And at the time, Linux has become popular. So he thought, why not build supercomputers by using Linux? So a classical supercomputer is a significant cost. It requires a lot of resources, and not only a few centers can support it today. If you look at the PC today, it's really high performance per unit. It's mass market, so that means that it's actually a low cost because there are so many buying PCs anyway. And also there's a very fast development because gaming today. So gaming actually produces some the GPUs that we can use for computing as well. And because there are so many people gaming, graphics card is really lower cost. And that by using PC and that kind of hardware, you can actually build very cheap supercomputers. And in 1993, Donald Becker and Thomas Sterling actually tried this. So in 1993, Linux was quite new, but it could be installed on normal PCs with a 486 normal hardware. And what also enabled this revolution is that the compilers for compiling your software was free. The Linux operating system was free, and it could be you didn't have to have a graphical desktop or anything. You could just run a basic operating system on a server just to be able to run computations. And also some of the standards for parallel programming enabled you to actually move from mainframes to PCs, because you could actually program them on a normal PC. And that enabled you to actually create really cheap supercomputers by just using commodity hardware. And that is actually, I would say, almost all supercomputers today derive from this technology. Even Cray today builds their supercomputer using Linux, using GNU compilers, using MPI for programming. Those three parts, even if they have some special networks, they are still the same basic architecture of this. The previous computers that we showed you, the Roadrunner and all these, were custom hardware. So this is enabled a revolution. So it's very cost effective to build a high performance computer because you can actually buy normal servers that you use in any other IT and use that as a base. You have many suppliers that can supply the parts. The things that are a bit negative is that you can't build large machine with shared memory because it's you can buy a single machine with large memory, but there is a limitation on how many processors you can have in that machine. And also networking can become quite expensive if you want to have really high performance. And also there is a higher error rate on certain PC hardware, so it can fail more often. Just want to do a quick here. This is so there is an organization called Top 500, which every year in November publishes the fastest computer in the world. So there is a competition. Every time they go to a conference called Supercomputing, vendors and universities submit the results here to compete on becoming the best computer in the world. And they make statistics of this. So you can see here that the different architectures that you have. So if you start at on the left side is 1995, you had Constellation, that basically mainframes, single processors here. You have single instruction vector computers here, and it goes away, replaced by multi-processor computers here, dedicated ones. But the Linux clusters here is the blue parts. So you can see here around, it started kind of here in the 90s with Donald Becker, and then you can see it's formally exploded here. So the blue part is actually the normal Linux clusters. Operating systems. So if you start here on the blue side, we have Unix. And Unix was a commercial operating system used by IBM and Sun and others, big computer manufacturers. They developed them themselves. And you can see here the the pink part here, that is Linux. And you can see here that from mid-90s, you have an explosion of, so now basically everything is running Linux. There is no dedicated special supercomputers running their own operating system anymore. And here you can also see some how many cores per socket you have over the development here. So you can see that it's started with a single socket here, and then you can see the increase of sockets in every server here. And here's different processors in the systems. And the majority now is, let's see here, I would say some kind of Intel architecture here. Okay, accelerated coprocessor. What is happening now in the industry is that we get more clusters that doesn't only have normal processors, but they also have accelerators at GPUs. And that is, today it's very related to AI and machine learning, that which is run best on GPUs or graphics cards. Skip that here. And here are some interesting on the performance of performance development, where we are. So you can see here in 1994 we had a range. The sum of all supercomputers was 1 teraflop, and the usual cluster was around less than 1 gigaflop. Today we are approaching exaflop range with the supercomputers. So you can see here that 101 petaflop is a standard cluster in 2018. That is kind of with Cosmos, and now the sum of all is in exaflops. And now we are talking about the biggest machines in Europe will be exaflop machines. So it's quickly, and you can see there are some trends here that it's actually the development is actually slowing down, and that is because it's hard to cram too many transistors on a single processor. That gets too hot. So there is a discussion in how to actually increase performance over time, because of this is not sustainable. At some point we will need a nuclear power plant to operate a supercomputer, which is kind of not realistic. So how do you use clusters? Yeah, there are many ways. The classical way, which has been used since the 60s, is using a terminal to log in. You get a command line. It's like when you type the conda activate, that kind of interface. You enter commands. But you can also, which we prefer today, is to use a remote desktop connection. When you log in, on that machine that you log in, you have access to your common high-performance computing software. You have compilers. You have your Python interpreters, Anaconda, which you are using in this course. There is a file system that is available on all compute nodes or servers, and you upload your files to this machine, and then you work on that machine and download the files when you're done. What is a bit different from your normal computer is that you can't start your programs directly. So what you usually do is that you define a script which tells the queuing system or the cluster what you want to do. And then you submit that script to your queuing system. And it schedules your job to run when there is enough resources and if you have time to run. So the queuing system is like what's it called? Calendar, where you can book time, and then but it's automatically scheduled to run your jobs when there's available resources. So here's an example. It's a batch script. There are a lot of things here, but these keywords here are how much time do you want to have. So you always have to specify how long you estimate your run to be, because it's not possible to start anything and just run it. The queuing system will kill your job when you exceed your time. You can name your job here. You can specify the output of your job. You can load your software here, and you can execute your code here. So in this case, it could be your computation, your parameter study as the final here, and that you submit to the queuing system. And the queuing system takes your job here. It is in a bin here. And there's something called a scheduler that looks at incoming jobs and looks at how many servers they're required in parallel, how long they are, and it tries to schedule them in a calendar here to run as optimal as possible. So on the left side, you can see all the nodes. So 1 to 252. And then it tries to put the jobs so that it optimizes the queue and reduces the queuing time as much as possible. So I will see if I can just do a quick through of the LUNARC history of our clusters. So LUNARC is actually a center that was founded by computational chemistry, computational mechanics, and computational physics. And today it's actually many more institutions at the university that is part of makes LUNARC. It's a center that is available for all researchers at the university. So the current systems we have today is Cosmos is 182 nodes with every server has two 24-core processors, AMD. So in total we have 8,736 cores or CPUs, and there is 256 gigabytes per server. So the servers are these racks here. So this is one server, this is the next server, and they are inserted into a rack. And these black cables here are the InfiniBand network that connects the servers together. The white ones are normal Ethernet connections. So we have multiple networks here. We also have a special cluster for sensitive data for doing computation on human DNA or medicine data, which has some restrictions on how you can access the internet and so on. This is our first PC cluster. Doesn't look so nice today, but it was built by using beige boxes, which we bought on the local computer store, a lot of them. And we connected them together with networking manually. So it was a home-built cluster. So this is one single server in the compute cluster. There was a network connection. We didn't connect any displays. And everything went into a switch. So this is actually what you need to build a cluster. It's a switch with network connections, a lot of servers, and then you kind of have a queuing system that schedules these servers in different ways. So this was an AMD cluster, single core processor per desktop machine. The next cluster we built, we realized that we shouldn't buy big boxes that are empty air. Could we kind of build it more compact? So we bought a lot of Dell small form factor PCs and connected them together. So total 7 was, we actually bought 128, so that is 2 to raise to the 7 a bit. It wasn't me who decided this. So this is the computers. They all actually came with a Windows license. So we had even if we run Linux on them, we got a Windows license for each of them. And it didn't look as bad when we built it first, but this cluster was moved from IKEA Ivarhyllor to steel shelves because LSE wouldn't allow us to have wood in the computer room. So we had to change shelves. So that's why the cabling to the network in here is a bit complicated. And here is a console here, so there is a machine you log into to manage the cluster. But it's basically a lot of machines connected to the network which are scheduled together. Yeah?
Which year was that?
This is in, I think it's 2002 or something like that. So Sigrid was our first rack mountable system. So this was part of the LHCK project or VLCG, this CERN project accelerator. And Sweden bought a lot of nodes in Sweden that for computing locally in Sweden the results from that experiment. And these are rack-mounted single processor servers. So we had 100 servers in the compute cluster. And it had a lot of cabling. It was actually one of the first computers that we can actually remotely manage, log into the servers and manage them remotely, even the hardware. Docenten, 210 nodes, Docenten, it's very original. AMD processor, 64-bit, first cluster. The part here in the middle is the login server, and here are some storage server that provides the file system. A lot of cables as well. Really hard to get all the cables into the switches because you have, complicated. Milliotto was our first cluster with more than 1,000 cores, so it had 252 nodes with quad-core processors. It used IBM Blade chassis, so this was almost a mainframe machine. So this is a Blade chassis. Cabling again, a lot of network cables. We also had to put extra cooling on the back here. So this is a backpack that cools the exhaust air with water. Then we had Siri, which was our second grid cluster. And the CERN project generates a lot of data, so there's a lot of storage servers here that are just for storing local cache data from the experiment. And then we have Dell Blade chassis here for the computing part. And these are Blade servers that was used in the Siri machine. So you can pull one of these out. Each of these parts here are single servers that you can pull out and manage. Then we had Plato, which was 20 teraflops. And here we actually have a new cooling solution here. So this rack in the middle is actually a cooling rack. So it blows cooled air in front of the servers and pulls in warm air in the back, and then it cools by water here. So we could have each of these racks can have 35 kilowatts of servers in them. And we still have many of these racks still for cooling even the Cosmos machine. Alaric 40 teraflops. And then we have, Aurora was 240 teraflops. And then Cosmos, this latest one, 1 petaflop. So HPC is an important tool for science today. I think many of the science areas can't do without high-performance computing, actually, especially in chemistry. Actually, they allocated for the COVID research, they allocated some parts of the supercomputings in Sweden for simulating drug development. Enable more simulation shorter amount of time, reduce expensive real-world testing, enable AI and machine learning, which is the biggest growing trends today in supercomputing.